Let's start a new chapter today, something called as partial fractions. And like always, before jumping into this topic straight, I would like to take a step back and give us some orientation and set the context of what the topic is all about and some of the terms and terminologies that we might have done in our elementary school, but it does not hurt to do a quick refresher on that one. And in that regard, in the context of partial fractions, one of the important concepts, the whole partial fractions revolves around something called as polynomials, which we must have learnt in middle school or maybe late secondary school. And back then, we would have done a lot of mathematical operations around polynomials. But since the whole partial fraction is centered around polynomials, it's a good idea to have a quick refresher. So let's do a quick bite of video today. And in this episode, let's just talk about polynomials. Let's get the basic facts correct and let's get some things clear, at least whatever is relevant in the context of partial fraction. And then in the next episode onwards, we'll jump into the actual syllabus of what partial fraction is and how should we compute that. Okay, so let's see what we have got today. Okay, so what I've done is I've taken some sample expressions which are polynomials, and I've put it over here: 2x plus 3y, 2x, and 4x square minus 5x plus 2. All these are independent equations or expressions. And let's focus on one of them. Let's take the last one as an example because that has a nice combination of a lot of other things. And let's see what are the key ingredients of this equation and what do we have here. Okay, and I've color coded for ease of reference. Okay, so we have 4x square minus 5x plus 2, and each one is color coded, and that is each color code kind of is referring to a particular terms that we'll be using in the context of a polynomial. And let's take it one by one. Okay, the first one is, let's take any term, this whole thing which is in circle, right? Whatever you see in circle, which is either before or after the arithmetic operation, which is plus or minus. Whatever is this symbol, this whole thing that you see in circles, there are 3 circles. Those are called as term. Each one is called as term, and this has got 3 terms. There are 3 circles, and the divider between them, each term is either the plus or minus operation. Okay, not the multiplication, because 4x square is nothing but 4 into x square. There is a multiplication, so we will not count the multiplication as a separating operator. But whatever is the plus or minus, whatever is between those operators or next to the operators, that whole bunch will call as one term. So this whole circle is term 1, this another circle 5x is term 2, and this number 2 is term 3. That's the first concept. And the second thing is, wherever we have the variable x or y, it could be multivariables, it could be one variable, we have variables which are unknowns. So those are called as variables, which is x, or the unknowns basically, which is not determined. In this case, there's only one unknown, which is x, and that's called as variable here. So we have a variable here which is in the purple color or in the violet color. Over here we have the variable 5 here. That's one. The one in orange, that itself is an operator, plus or minus, that's called as an operator. So in mostly it's going to be mathematically plus or minus only, that separates the terms. So we're going to call that as an operator. The number without the variable or without the unknown, the number by itself is called as a constant, which is in green color. So we have covered this. And whatever number we have associated with the variable in terms of multiplication, this is like 4 into the variable. This number is called as a coefficient of the variable. So we have covered this. This 5 also is a coefficient. So whatever you see in this blue color, that's a coefficient. We have covered that. And whatever is the power of the variable, in this case, the power of variable x is in yellow, and which is 2, that's called as exponent. In this case, the power is implicit. It is not written, but it's 1. Again, this is an exponent. In this case, 2 can also be written as 2 into x raised to 0. And again, this 0 is an exponent. So whatever is in the power position of the variable, that's called as an exponent. So we have covered that also. So we have covered coefficient, we have covered variable, we have covered exponent, we have covered operator, we have covered term, and we have covered constant in this case. Okay. So like we saw that each of the above expression has all these things: terms, mathematical operations, plus or minus between terms, and x within a term itself, which is multiplication. This is multiplication, not x. And then coefficient, variables, constant, and exponents. So whenever any expression has a combination of all of this, like what we discussed, that expression is called as a polynomial. And this is kind of the Wikipedia definition of what a polynomial is. But in simple words, anything that has a combination of all these things that we discussed or we showed in color coding, all of these ingredients, whenever you bring these ingredients in this particular fashion, that expression is called as a polynomial. And what is the literal definition of a polynomial? Poly means many and nomial means terms. So expression of many terms, that's what polynomial means, an expression of many terms. Okay. And is it necessary that you always need to have many terms? Not really. If you see the example over here, these are the different types of polynomial based on the number of terms. So let's say you just have this one term, and remember the term is nothing but anything that comes between the plus or the minus sign, and there's just one term, there's nothing else. So in this case it becomes monomial, where it's just one term over here. If you see the next one, that's a binomial, and like the name suggests, there are two terms. This is a plus operator. It could be a minus operator also, but minus or plus based on the operator, how many terms are on each side. There is term 1 here and there's term 2 here. That's why it's called as binomial. It has got two terms. Similarly, if you see the next example, there is a plus symbol here, or there's a plus operator here, and there's a term 1 here, there's a term 2 here, and there's a term 3 here. And that's why it's called as trinomial, which is because tri means 3, it has got 3 terms. And anything that has got generally more than 3 terms, it could be 4, 5, 6 infinite terms, that's called as polynomial, because over here if you see it has got 4 terms, which is between plus, in this case there's a minus symbol also. So it can be a plus operator or it can be a minus operator. And adjacent to those things, each one is called a term. So if you see there are 4 terms here, 1, 2, 3 and 4. And hence it's called as polynomial, meaning that it has got more than 3 terms. But in terms of normal day-to-day language, anything which is more than 1 term, it can be loosely referred as polynomial. Although it's not the strictest definition, the strictest definition is anything that has got more than 3 terms. 4 onwards is called as polynomial. But for the sake of this context, anything that is more than one expression or one term, if the expression has got more than 1 term, we'll just refer to that as polynomial. Okay. So that's another concept. And there are some examples which are not polynomials, and let's see what are those examples here. And the polynomial cannot have an exponent which is negative. Say this is negative minus power. That's not a polynomial. A polynomial cannot have an exponent which is in a fraction. So when you say root of 7x, which means that it's a root of 7x, let me hold on. It's a x raised to the power half. So it cannot be a fractional power. So what is root x means? 7x means 7 root of 7 and x raised to half. It cannot have a fractional exponent. That's not counted as polynomial. The variable cannot be the exponent itself. So this variable x is unknown and it cannot be the exponent itself. That's not as counted as polynomial. Over here again it's negative, it's not counted, same as the first example. And over here also it's negative and fractional, so not counted. So these are some of the examples which do not constitute to be called as a polynomial. And rest all of this you can see as a polynomial. There are 2 terms here and x does not have x, the power of x is 1. It is just 1 term here, monomial, again the power of x is 1 here. And this is like there are 2 variables x and y, and that is okay. And again these are like there are 2 variables in each term. This is 1 term, this term 2, this term 3, this term 4. And the first 3 terms have 2 variables each, that's okay. Here the x has a positive power, that's also okay. So all these examples kind of fit in the definition of what is called as a polynomial, and all the examples on the right which I showed predominantly are not defined as polynomial. In the context of partial fractions, we'll be just sticking to this kind of definitions which are truly polynomials. So just a quick side note on that one. Okay, and that's one most important concept which is going to be the essence of solving all the examples on partial fractions, and that is called as a degree of a polynomial. Degree of a polynomial. And what is the degree of the polynomial? So degree of the polynomial is nothing but what is the greatest exponent of the unknown variable, whether it could be x, it could be y, whatever is the variable, whatever is the highest power, and there is a way to calculate the highest power. That highest power is called as the degree of the polynomial. Okay, and why they have written as monomial with greatest exponent? Because each thing you have to take as a term. Let's say this is term 1, then there is term 2, and there is term 3. So each one individually is just one term, right? And if the polynomial has got just one term, it becomes a monomial. So polynomial is nothing but a combination of a lot of monomials. So this by itself is a monomial, this by itself is another monomial, and this itself is another monomial, right? So we have to take each term. What it means is taking each term within the polynomial or taking each monomial separately before the plus or the minus sign, and whatever is the highest power for that term, that becomes the degree of the polynomial. So we'll take the degree of this, we'll take the degree of this, we'll take the degree of this. So we have got degrees of each of the terms or each of the monomials, and whatever is the highest among all of this, the highest exponent, that becomes the degree of the whole polynomial or polynomial as a whole. So let's try to understand what we are trying to do here. Let's take some examples, okay? So now let's take, we have a polynomial, we just have the number constant. Yeah, that's possible because we saw a polynomial could be a combination of any of these things. And we just have a constant here, the one in green color over here, right? And a constant means it's as good as multiplying with an unknown variable with a zero exponent. So what does 9 mean? 9 can also be written as 9 into an unknown variable raised to the power 0. That's also is okay. So in this case, it is just one term, just one monomial, there is no other terms, okay? And what is the exponent or the highest exponent of that one term? X raised to 0, the exponent is 0. So the degree of this whole polynomial becomes 0. That's how you compute it. Let's take this example. It's simply as is written as x plus 4. So there are two terms. There is one term here and there is one term here. This polynomial has got two terms or two monomials. It's made up of two monomials. This one is constant, so we don't have to worry. It is as good as x to the power of 0. And so we should take the degree or the highest exponent for each term. For this term, the highest exponent is 1 in red color, and for this term it's 0. And we have to take whatever is the highest exponent for all the terms put together. So the highest is 1, which is associated with this first term. Hence the degree of this polynomial is 1. Let's take another example. Now we have got three terms here. This one term, this second term, and this third term. And the first term, the degree is 2. The second term, the degree is 1. And the third term, the degree is kind of x raised to 0, 0. So now we have got 2, 1, and 0. Three terms, and we have got 3 degrees. So what is the highest degree for the whole polynomial? The highest degree is for the first term, which is 2. And hence, the degree of this polynomial as a whole becomes 2. Same way over here. We have got term 1 and we have got term 2 here. And the highest degree is on the first term itself, which is 3. And hence, the polynomial degree as a whole is 3. And over here, if you see that it's tricky, and I put some more examples here. The first term has got two variables. It has got two unknowns, x and y. And there's a second term and there's a third term. So it has got 3 terms. This term 1, term 2, and term 3. Okay. And whenever you have two variables or more than one unknown and they have some exponents, the trick is you should add them because this whole thing is part of one term itself, right? So you have to add the exponents. So 2 plus 3 is the exponent of highest exponent of this whole term, which is equal to 5. And over here, the term is second term, the exponent is 4. And the third term, there is no exponent, it is just 0. So now we have got 3 terms, and the highest power is this, 2 plus 3 is equal to 5, and hence written as 5. So the trick is, if there are multiple variables within a single term, then you have to add the exponents because we need the highest exponent of the term as a whole. Then we'll find it for each of the term, and then whatever is the highest of all of them, that will be the term or that will be the degree of the polynomial. And that's what I've written here in red. Degree of a polynomial should be counted after combining, meaning after adding the exponents of all the variables in or within a term. What does that mean? This is the term, okay? This one thing, which is whatever is before or after the plus or the minus operator is one term. So this x raised to 2 into y raised to 3, this whole thing is one term. So in this case, you need to add that because we have got two variables and hence we need to add the powers to get 5. And I put some more examples to make sure that we understand this. Although I don't think there are going to be any trick questions in the exam, but it's better to know and get this concept clear. So we have taken some examples and I put some degrees here to know how should you think about that. Okay, so what is that? What is the deal we are trying to talk here? Degree of a polynomial should be counted after combining, which is adding the exponents of all the variables If there are multiple variables, then all the variables in or within a term itself. And whatever is the highest, we should take that. So let's try to apply that logic, which is written in red color, to some of these examples. Okay, so this is x raised to the power 2. There's only one term, and what is the highest power? It's 2. So this is not negative sign, this is just saying it's a degree. So the degree is 2 over here. Now let's take this example. This has got two terms, right? Over here, x square plus 4. This is term 1 and this is term 2. This is term 1 and term 2. And term 2 is as good as saying that x raised to the power 0. So what is the degree for the first term? 2. What is the degree for the second term? This is 0. Okay, now what is the highest degree for the terms? 2. And hence the degree for the polynomial as a whole becomes 2. Okay, now let's take this slightly tricky example. So we have here, let me rub this out here. We don't need this so that we don't get confused. Okay, so let's try this. So we have got x square plus 4x. So we have got x square plus 4x. Okay, so we have one first term here, we have the second term here, because we have the additions operator in the between. So we have got two terms. What is the degree of this term? The highest degree of this term? This is 2. Okay, this is 2. And over here, what is the degree of this? This 1. Okay, but we just need to know the highest of all the terms. So in this case, there are two terms, and this degree is higher. So the polynomial's overall degree of the polynomial will become the highest one, 2, and hence this is also 2. So that's how you need to this thing. So we need to just be careful whether we are looking, what is the operator that we are looking at. If the multivariables, like over here, if you see, that's a part of the same term, it's not across terms, hence we add them. Over here, this is separated by a plus or a minus sign, so these are two different terms, so there is nothing to add. We just take this term as a whole and apply that. Okay, now let's take this. Now this is like x minus 2 the whole square. Let me remove this so that we get more clean real estate. Okay, now we're talking about this example. Okay, the degree is 2 here. How does the degree come here too? So let's see, we have got x minus 2 the whole square. Okay, now we need to find the power of x as such. This is not the power of x yet, it is a power of a whole different term. So if we expand this, we get x square plus 2x plus 4. Okay, now we have got three terms here, 1, 2, 3. This becomes a quadratic equation. What is the power of this term? This power of this term is 2. What is the power of this term? X is just, if you simply write x, it becomes x raised to 1. So the power of term is 1. And this is as good as writing x raised to 0, and the power is 0. Now for each of the term, which is the highest one, this is the highest one. And hence the degree of the overall polynomial becomes 2, which is what is written here. The degree of polynomial is 2 over here. Sorry, we're looking at here, sorry, not this one. So yeah, we jumped it. Okay, the degree of this polynomial is 2 here. Okay, now the same this thing over here, we have got x square minus 4x. This is the same example as this. The only thing is, in between there is a minus sign, but the highest degree is in the first term itself, and hence this degree also is 2. Now let's take, I mean, coincidentally all the degrees are 2, it is just by coincidence, but if you can understand the drift where we are going with that. Now we have got x plus 1 and x plus 2. So we have got, if you expand this here, it will be like this, right? So it will become x square plus 2x plus x plus 2, which will be x square plus 3x plus 2. Okay, now we have got three terms here, 1, 2, 3, and we know this the first term has the highest degree, and hence this term is 2. That's how it is, right? So same way, if we do all the things, we get a notion of degree. The last two examples are slightly tricky. Let's focus on that. Okay, so this is also pretty straightforward where the degree is 2. Okay, now let's look at here. These examples are very tricky. So let's focus on this example. X minus 2 the whole power of 7 multiplied, this is multiplication sign, and then x plus 1 the whole power of 4. What is this? The degree I have written as 11, but how do we get that? So if you open up this bracket, there will be a first term will have the highest power, which will become x raised to 7, and then there will be long terms, but we are not worried about all the terms. We just need the term with the highest power. The first term itself will have, like how we had over here, when we kind of simplified it, we had x square with the highest term. The first term itself has the degree of 2, whatever is there. Similarly over here, the first term will have a degree of 7, and then it's multiplied by another expression which will have a degree of 4, because the first term, even if I expand it, the first term will have a degree of 4. And whenever we have in the same term variables getting multiplied, so we just add the exponent 7 plus 4, and that's is equal to 11, and that's what the 11 comes. And that's what kind of we learned here in the red color, that we should just combine those exponents if it's coming up as a part of the same term. Okay, that's what it means. Similarly over here, let me clear this off. Similarly, if you see the next example over here, we have got, I would not say we have got 3 terms because this all are multiplication, but assume that there are 3 kind of subterms, or there are 3 kind of mini monomials, expressions, or whatever you want to call, but they are not individual terms because the individual terms has to be between plus or minus operator, right? But if you take this, the highest power of this particular piece is going to be x square, and hence the power is going to be 2. The highest power of this particular thing, it's all multiplication. Again, this is going to be x square. When you expand this is going to be 2, and this has a power of 1, and hence we have added this. And since it's all multiplied, we need to add the exponent. So this becomes 2 plus 2 plus 1 is equal to 5. That's how it is done. Similarly over here, this is going to be another tricky example. It is x square, and then the whole expression is again raised to 2. So when you expand this 2 gets multiplied with this 2, and the highest power, just expanding this, the first term will have x to the power of 4, 2 into 2. So that's why I put 2 into 2 here. And then for this term, the power is 1. So I've got 1 here. And for this term, again, if you just expand this, the highest power and the first expression, or the first, when you expand it, the first power exponent for this x will be 2. And again, I've got this 2. And since each one of them is multiplied, we just add the exponent. So this 2 into 2 is 4, and this is 3. 4 plus 3. So the degree of the overall polynomial is 7 in this case. Same, different type of example, but same concept here. And here is something that interesting that we need to see. For example, over here, if you see, just take this, when you expand this x to the power of 2 will be again raised to the power of 2. That will become 2 into 2, 4. We get it here. Over here, if you see, it's multiplied by a new kind of expression, which is x minus 2x. In this case, right, like for example, in the previous one, there was no x here. It was just x minus 2. Over here, it's x minus 2x. So the difference is we took the power as 1 here. Here also we'll take the power as 1 only, because we just need to take the highest power. So this has the power of 1 and this has the power of 1. We are not going to do any addition or subtraction because it's separated by an operator. We'll just take the highest power, which is 1, and we have just kept it. So although both are different expressions, the power is still the same. And I just wanted to highlight that we should not get confused with this x and add the power, because this is separated by a minus operator. Although it's not a term by itself, but this is like a sub term, and we have to just take the highest power. In this case, we have to multiply because this whole thing is multiplied by 2, and hence we multiplied it. And for this term, again, we have to just take the highest power of between these two, not everything, because this whole thing is just one sub term, and the highest power is 2. We have taken 2. We are just ignoring this power 1. We are not doing anything. So we have got 2 into 2, which is here. The highest power for this is 1, and the highest power of this whole expression is 2 here. We have just taken 2. Again, the power is 7. Okay, the same concept. So basically, that whatever I explained here, I've highlighted here. For example, if you have this, we have got the first 3 sub terms, if I can use a term, multiplied here, and then we have operator, which is what separates the term. So this whole thing is one term, and this whole thing is another term. So there are only 2 terms here, because that's how the operator separates. Either it should be plus or minus. And whenever you find the degree of this whole polynomial over here, we will take the highest exponents. Okay, and how do we do this? For the left hand side, for the whole term, we will determine the degree is 7 based on the previous example over here. We know how to do that. And then we have a plus sign, and the degree of this is 3. So the first term's degree is 7. Let's say we have got 2 terms. The first term's degree is 7. This is the first term, and this is the second term. Over here, this is the first term, and this is the second term. The first term's degree is 7, and then you have a second term whose degree is 3. So we'll ignore this, the degree of the overall polynomial, because we just need to take the highest degree, which is 7, and hence the degree is 7 in this case. So those are the examples of where you can get confused and how you should think about. I don't think there are going to be any complicated examples coming in this fashion, but now you know how to compute your degree and how do you kind of think when should you add the exponents and when should you just take the highest exponent. and primarily how you should think about the terms. What exactly is the term, whichever comes between the plus or the minus operator, that's the term, and that's how you should think about the terms. So that's kind of a quick refresher on what is the degree of the polynomial, a very important concept, and you will see that we'll be talking about this in the next few episodes, because based on the degree of the polynomial, the methods to solve partial fractions vary. So that's very important concept over there. Okay, what else we have? And as a quick reference, right, there is a nice video on YouTube which kind of explains all these examples in a nice way. So if you're interested in extra reading, you can go through this YouTube video. Okay, now let's come to the last subtopic on this polynomial expressions. So if you see polynomial expressions, they can also be termed as functions, and I'll explain you what it is. And why this is important is the different types of partial fractions, what are the different varieties that we are going to see, that will pretty much come from one of this, and that's why this is important, okay? And let's check out the different ones, like how we saw here, different examples, the same concept, but we will be just kind of assigning some names to them. So if the polynomial just has a constant, just one term, and the one term is constant, which is as good as saying that it's multiplied by a variable raised to 0, because anything raised to 0 is 1, so it becomes a constant. So the whole expression just has one constant, for example, just 4, nothing else, okay? So that expression or function is called as a constant function, and the degree of that is 0, because that's the highest exponent of the unknown variable, 0. And if you think from this as a function, meaning that if you plot this graph, this is how it will look like. If you see a constant in an x and y axis, we have a simple constant because it just does not have any dependency. It's very independent, and there's a straight line. For example, if it's 4, then this will be the point 4, and it just cuts through that. That's what constant means. So it's very easy to relate this with a function, so that whenever we do these functions, it will be easier what it means. Now let's talk about a linear function or a linear expression. And all these are examples of polynomials only. So a polynomial which has only constant, then this is the first example. A polynomial expression which is called as a linear. What does it mean? The highest degree will be 1. For example, if you see 2x plus 4, which is as good as x raised to the power 1. So the highest exponent is 1, because this is x raised to the 0. So this has got 2 terms, but the highest degree is 1. So any factor or any expression which has a variable, unknown variable, unlike the first example, which is only a constant. So we have an unknown variable and we have a constant, or we could just have the unknown variable, that's also okay. And if the degree is 1, then it's called as a linear function. And this is the classic example of a linear function. If you see here, a straight line, the value of x is dependent on y. So you just draw a straight line. When you change the value of, like, it's like saying that y is equal to x. Whatever is the value of x, y will become that, something of that sort. Then the next expression is quadratic, the nature of the expression. This we are very much familiar, because we have done this in the elementary school, where let's say we have got 3 terms and it's introducing power, and the highest degree is 2, and then 1, and then 0. The last one is constant. So we have got 3 terms, the highest power is 2, and it's reducing, and with the last term as constant. If that's the case, then this expression becomes quadratic in nature. Sometimes the quadratic can be factorized, and sometimes the quadratic cannot be factorized, but this is what a typical expression of quadratic is. The highest degree is 2, and there are 3 terms, and all of the powers are descending. This power of 2, this power of 1, and this power of 0. That's what is quadratic. And quadratic typically is a parabola or something like that, which is what this function is. If you see, it cuts the x-axis at 2 different points. So the degree is 2, it cuts the x-axis at 2 different points, okay? So that's what is quadratic. And the last but not the least is cubic, where you add one more term to the quadratic, because like the way you see is each one has one extra term. The constant has just 1 term, the linear has got 2 terms, quadratic has got 3 terms, cubic has got 4 terms, and the degree or the exponents of x are in decreasing order till you get a constant. So there is a pattern to that if you see each one of them. The cubic will start with a degree of 3, and then 2, and then 1, and then 0, which is the last constant. So there are 4 terms. The first term has the exponent of 3, and hence that's the highest one, and the degree is 3, like we have seen, and this is one of the examples. And if you plot this on a graph, a cubic function will look something of this sort. And this forms the crux of one of the important chapters that you will see later, complex numbers. Complex numbers kind of was derived because people were trying to solve this cubic function, where it cuts the x-axis in three different points over here, right? So anyway, that this is not relevant for partial fractions, but you can associate each one of this expression to the graph so that you know what we are talking about. So these are the four things that we'll be talking when we try to solve different types of partial fractions. We'll be using a combination of this and the concept of degree, whether the polynomial is linear or quadratic or cubic, and what is the degree of that. Based on that combination, there will be different methods that will be applied to solve partial fractions or expressing a polynomial expression into a partial fraction, and hence this was kind of important to refer. Okay, and as always, I put some references for which I referred and which I found useful. If you have time and if you are inquisitive, you can go through this. Otherwise, from an exam standpoint of view, whatever I've done, that's pretty much is good enough. So that's a quick wrap up on this particular episode where we talked about what is a polynomial and some fundamentals about polynomial, trying to understand in the context of partial fractions, and we'll talk about partial fractions in depth starting from the next episode. Thank you.